So today, what I'm planning on doing, I'm not going to have you buy another book, but I'm going to use excerpts from this book that was used during Stan Reeves' time. It's Cooper and Gillen, because it does a very good job in chapter 2 and 3 of showing you what the density functions are and what the distribution functions are. We'll come back to chapter 3 in this book. And does everybody have access to these texts?
I have the other book that you just had. I have the PDF copy of this.
All right. Now, as I understand it, I'm just going to tell you this. Dr. Bashir is in the process of selecting one book that this class will be taught by. So far, he's jumped around and has 2 or 3 different ones that he's referenced. And so what I'm trying to do is not make anybody buy books that are unnecessary. I know a lot of stuff is online, PDF and stuff like this, but I did want to let you know that. And today what I'm going to do is I want to finish up chapter 2 and then move into this density functions. Bradley Russell.
Sir.
Right.
Thank you.
And what I want to do is talk about the drug testing. First, this is in chapter 2. And the reason I'm doing this, a lot of these problems are very similar. If you thought about that binary channel problem, and then you looked at several of the other things, including this drug testing, the logic is the same. So let me do it this way. Every time I come down here, I'm a little suspicious. I will not have markers. When we're talking about it, and again, this is in section 2.5. If you want to take a look at your books, or if you have your PDF available or your book, does anybody have the book that we have? You got it with you, right?
Yeah.
It's section 2.5 in the book. And here he's doing a binary channel. Let me just explain something. When they're doing this, they try to give you a visual representation of what's going on. It'll make it easier to actually understand the problem and how we use Bayes theorem. He's going to say, for this drug testing business, we're going to have 2 people, and what I'm going to say is U equals 1 is going to be the drug user, and U equals 0 is somebody who's not a user. This is fairly obvious. It'll look just like the binary channel. And then we're going to have some things where he's going to say, if we do a drug test and the user comes over here and the test is positive, 1 means it's a positive drug test. The guy has failed, basically. Follow me? And I like to use 1 or 0s. I do not like a lot of the long way of describing things because I think it causes you to get distracted. And we're also going to have, if the guy isn't a drug user and it comes over here, T is 0. Now, what he will say, the way he does it is this. He does not have a probability of this occurring or this occurring. It's the type of thing that you don't want to happen, that he's going to actually give some, you might say, probability. And what he'll do here is, I believe he does it this way. He says if the guy isn't a user, but it tests positive, this is going to have a value of epsilon. Can you confirm he uses epsilon as that symbol? He uses V and epsilon. Do you see epsilon there? Or not? Anybody see epsilon? Do you see it or not? Or you don't?
I'm not a problem.
All right, now that means that there's 1 minus epsilon because the sum of these 2, if you think about it, has to be 1. Y'all follow me in this class? So if the guy is a user and he tests positive, or isn't a user, sorry, and he tests positive, it has a probability of epsilon, like 0.01, 0.02, hopefully. And if he isn't a drug user and comes out correct, that's 1 minus that. That's the only thing they're saying there. It's a binary channel kind of approach. Over here, if he is a drug user, but he tests 0, then they didn't identify him. So it would be a false negative. But this has a rate of V. Don't worry about the terminology. This is the only thing you really need here. With me? And that means it's 1 minus V would be the actual probability of him being a user and then it coming out Correct, right? Now hopefully V and epsilon are very low. But here's where, can you follow me back there? I mean, can everybody understand what I'm talking about? Now, then in the book, he's going to say, and there's a very important point here. It's very troubling, you might say. He's going to say that we'll assume that the number of people that are drug users is, or I should say, the percentage is P. It's not percent, but the actual probability is P. So here, P drug users, 1 minus P non-drug users. I hope that is confirmed in your book if you take a look. You've got your book open. Does anybody have the PDF open? You got your PDF. I mean, you got the book, right? You see that? Anybody confirm this?
Yes. Yeah.
Okay, now, what he goes through a little discussion. He says the worst possible thing is if you're not a drug user but you test positive. Makes sense. So what he's saying is, what's the probability of the test being positive but you not being a drug user? Follow me with the terminology. The ones and zeros are they just have to do with either success or failure of the experiment. So what is this equal to? And I went and I thought of the best way to show this. I always think about this. When we have P of A given B times P of B, that's equal to P of B given A times P of A. So another way, you all with me? I'm just showing you Bayes' law. What I like to do is take that P of B and put it over here. This is just me. So that's really what we're talking about in terms of two definable events. So what we want is this, if you look at this is my A event, and this is my B event. Now I could write a Venn diagram for this, but I don't think it's necessary at this time. I'll do it if we need it. You with me? So what do we need over here? Well, I don't know how far he goes into this in this section. If he actually he's going to have the U equal 1 crap with T equals 0, and he's going to have a whole bunch of different symbolism. Are y'all with me? So what I'm going to say is, well, U equals 0 is B, so I need, really, what? I need the probability of U equal to 0 down here, if you follow me. You all follow the
He's got the T and the U flipped in the textbook, where it's like U equals 1 given T equals 1. I'm not sure if that's like super.
No. U equal 1, T equal 1 is a different thing.
Or U equals 0 given T equals 1 instead of T equals 1 given U equals 0. He's just got the A
No,
and the
he
B.
wants this. I'm saying the user fails. So you is not a user, but the drug test comes out plus.
Yeah, he's saying that the user they're not a user given the test failed.
He solved for that first, I guess.
What?
He solved for the not a user and failed drug test first. In the book, that's all we're saying.
Just in the
That's
book.
all we're saying. in the book.
We're gonna get all that. Okay, I know
Okay.
where you're at. Just
Okay.
follow. This is what they want ultimately.
Gotcha.
That's where they're going. So, and I'm just defining it. So this right here is P. This is event B down here. So I'm making sure I'm clear about this. That this can get a little confusing when we only have two possibilities. If we got three or more, it gets a lot crazy. But you gotta understand the rationale. So now on top here, I want P of U equals 0 given T equal 1 times the probability of T equal 1. I hope that makes sense to everybody. All right, now I'm just restating what I've done over there, but now I'm defining the events, A and B, clearly. Now, how do you go about getting this? Well, what is the probability of U equal 1? If you take a look at this, U equal 1 is the drug test, right? That's just P. He says that's the assumed rate or the probability, so it's P. Now, if I take a look at the probability of the test equal 1, follow me on this. And I think everybody's going to get this. I'm just trying to explain this as easy as I can without making a lot of noise, you might say. If I want the test equals 1, what's the probability of this event occurring times 1 minus v plus the probability of this event occurring times epsilon? Does that make sense? So if I take a look at this, this is really the probability. Now I'm going to just, well, I'll put it down. So it's the probability of u equal 1, all right, and then it's going to be times 1 minus v, and it's going to be plus the probability of u equals 0, and then it's going to be times epsilon, because this is the cross, this is the rate that the user, is non-user is actually identified as he fails a drug test. Just take a moment. Y'all with me on this? Okay, now I put in the values, so what do I get? The probability of u equal 1 is just p times 1 minus v, and it's plus the probability of u equals 0. What is that?
P minus 1 minus p.
1 minus p. 1 minus p times epsilon. So now I have the probability of p equal 1, and now I need the probability of u equals 0. Did I do that wrong? No, I think I did. Of u equals 0, given the test equals 1. All right. So we're assuming we're down here, right? And we have this, and we want to know the probability of test equals 1 would be epsilon. Do you agree with that, everyone? Y'all follow the reasoning on this one? Blake, did you see this? I mean, I want to make sure I'm not leaving anybody uncertain about this. So this is just going to be epsilon. Now I'm going to come over here and put the thing together. So the probability of the test equal 1 given u equals 0 is equal to the probability of u equals 0 given test equals 1, which is epsilon. And then it's times the probability of test equals 1, which is going to be p times 1 minus v. So p times 1 minus v plus 1 minus p times epsilon. And it's all divided by probability u equals 0. Didn't I put that down there? Okay.
Well, that's just 1 minus p.
Yeah, that's exactly right. 1 minus p. And I'm sorry, you know what? I think you're right. I did the inverse. I'm sorry. I'm very sorry about that.
I mean, but this is still valid, right?
Yeah.
The base theorem still holds, base theorem is still correct. This is still valid if we wanted to find the probability of, what's that, a test positive?
Given
in a
u is 0,
non-drug.
but isn't that what he asked for?
He asks for u equals 0 given t equals 1.
Oh, and I got the inverse.
So the process is still the same, it's just.
Yeah.
But I want that one. Let me
Yeah.
just write it up here. I'm sorry. Let me do it over. That will work. I will. This thing. I'm sorry about that. Let me just put this down. So. Wants the probability of u equals 0 given a test equals 1. I'm sorry about that. Now I'm just going to rewrite what I did a second ago, okay? I'm going to restructure. So if I look at that, I know on the bottom here, it's going to be probability of test equal 1. I know that because this is P of A given B, and if you think about this, A is going to be u equals 0 and b is test equal 1. So that means the probability of b is probability of test equal 1. That's my point about this. Then over here, this is probability of a test equal 1 given u equals 0 times probability of u equals 0. Sorry to put this upside down. Do you agree with this, class? All right, now, let me go ahead and fill this in. So, real quickly, probability of test equal 1 is just p. I'm sorry. It's going to be equal to p times 1 minus v. Let me write this down here so I'm clear. Here's what I'm doing. Probability of the test equals 1. Well, it's the probability of this occurring times this weight plus, so it's going to be p times 1 minus v. And then it's going to be plus the probability of this occurring, which is 1 minus p. And then it's times probability of u equals, of epsilon, right? So now we have probability of test equal 1. Now probability of test equal 1 given user equals 0 right here. That's going to be epsilon. And then it's times the probability of u equals 0, which is going to be 1 minus p. You agree with that, everyone? Okay. I believe this is what he has for that, if you confirm it. Y'all follow me? Some of this gets a little irritating because of the notation, but if you just follow me on this, it's important to see is, one thing you'll notice is, just follow me on this. This and this are identical. So you can divide top and bottom by that. And then you get 1 over 1 plus, that's going to be p times 1 minus v over epsilon times 1 minus p. I did this on purpose this way. You with me? Just take a good look. Here's his point. If we're talking about a drug testing, and they have to have some sort of statistical information where they can gather enough data so they have an idea of the number of people out of the population that uses drugs. If they don't do that, then this whole thing's for naught. You all with me? Their drug testing, they probably cannot identify the likelihood of a false test versus a correct test simply by the method used and knowing, I guess, the chemistry and things like this. And I'm not an expert at this, but in his book, did anybody read the discussion on this, by the way? It is really one of these things where it makes you wonder, but they say if this fails, this test, and I don't know what kind of testing, they'll give you a more comprehensive, a more, I guess, expensive test, because there's going to be a lot of false positives. So just out of curiosity, suppose P is equal to epsilon, all right? And if you have that, let's let it equal to, just for kicks, 1/10, something easy, 1/10. So if P equals epsilon, it's 1/10. Then I have 1 over 1 plus, since P is equal to epsilon, what else? I'm sorry. Yeah, that's right. And as equal to V. I think that's how he talks about this being the thing where you assume that the rate of a non-user being found a user is the same thing as a user being found a non-user. And if you assume that, and you assume the probability of the drug use being 1/10, then you get something like this. And I'll get out of your way in 1 second. So you get plus, and this, P, which is going to be 1/10. The only thing I'm doing is calculating this times 1 minus V, and that would be 9/10 over, and then it's going to be epsilon, which is 1/10, and then it's going to be 1 minus P, which is 9/10. So that's 1. And that means 1 plus 1 is 1/2. So there's a 50% chance that if you get if you test positive and you're a non-user that's failed, all right, and you can jiggle these things. He actually has a graph in the book where he shows two values of P, the actual rate of the population that isn't a user and the failure rates. And he graphs this, but then he makes a real point that if you jiggle this thing a little bit, you're going to find that instead of having 50% of the people testing positive or that aren't drug users, you can jiggle that thing up to 80 and 90% possibly. Now, I've had lots of drug tests in my life for security work and stuff like this, tons of them. Usually it's just urine. I've had a few blood tests, but I don't know if they actually use that information. I don't know what kind of
It's
stuff.
usually only like in criminal, like
This
criminal
is
events.
classified work. I mean, for anybody here cleared, if you've got a clearance, you know, it's usually just a urine test. It's an unannounced urine test. That's the one thing you get. But what I didn't know is this. And I've never been in trouble for anything, but a very odd feeling, if you were, you know, knowing that this might not be accurate.
Yeah.
Did anybody ever fail one of these things?
Well, no, but I was in like traffic for one day and somebody went up there and he was appealing his I think he was on probation for it or something. And he had got a false drug test and he got his own independent drug test and the judge accepted the independent one since it was I think it was a hair sample. And he said he knew it was false. He was false.
I'm in trouble.
It's not reassuring, you know, you're ready for a job.
You're going to find two things nowadays that they do, and they do it here at Auburn. They have people that they pay to comb through the social media and see anything, any posts and stuff like that. If you put anything up there that is derogatory about race, religion, politics, figure out something that the media's hot button issues, they're not going to touch you. And the other thing is, if you have, if they catch you with anything where you have a gambling problem, I know gambling's legal in a lot of, but you can forget it. I mean, you can just forget it. And of course, drugs, because it doesn't matter what they say about pot and all that. If you test positive, I mean, you know, there's stuff, the CBD oil, you know what that is? It's for pain. Now, I've got plenty of pain, but I realize that if I'm going to use any of that kind of stuff to manage it, it has to be something called CBD isolate that is THC free. A lot of this stuff has a
And
low
even
level,
that has a little bit in it.
just enough, so if you're a police officer, they'll catch you and you will be let off without question. You don't get a trial because you're an employee of the state, so you're gone. You can't appeal that one either. I didn't know that. Anyway, some information may help you. So I'm warning you about this. Social media is not your friend. You can yell all you want about Alabama football, but man, be careful about yelling about politicians or anything else, because they're serious. Okay, that was in a nutshell. This is actually not a bad problem to show you how to go about setting it up and stuff. It's just basically. So there were two. I mean, we did the binary channel one, but all these problems where it's just two decisions: either you are or you aren't, and something else like this test fails or it doesn't. Those are easy. It's when you get to three or more possibilities. That's when it gets. That becomes much longer, and I'm not going to go there yet, but I will go there. So, let's see. I think in 2.5, there's a problem. Wait a second, where's that problem? Did I not have it? I think it's 2.10, because I don't have it. I think I left the other note sets of my car. I think it was problem 2.10. Isn't this the one that asks you to calculate several of the other probabilities?
It's like a network problem? Is that what you're thinking of?
What's
Solve network showing
2.9? It'll reference section 2.5.
Yes, that's 2.9.
I'm sorry, 2.9.
Continue the development in section 2.5
let's do, let me ask everybody, just go with me on this one, and I want you guys to think through it, that way I'll know it, you've got it. And I'm gonna put back up the diagram that I made, u equals 1, you can do it the way he does it if you want, but I don't like that. 0, this has probability of p, this is 1 minus p. The direct link here, test equals 1, test equals 0. Cross right here is epsilon, cross right here is v. And this is 1 minus epsilon, this is 1 minus v. So those are the relative weights of the actual guy being a user and testing positive. I'm just trying to show you this again. And it's nice to have a picture, trust me, of these things. It keeps you straight. So what's the next one he wants?
So the first one is u equals probability of u equals 1 given t equals 1.
Given t equal 1. All right, now, first I'm going to just set this up. Remember the P of A, B business? So right off the bat, here, P of A, all right, is going to, or this, t equal 1 is what I need on the bottom here. P of t equal 1. So it has to be in the denominator. You know why, everyone? Right? From Bayes' theorem, that would be over here normally, times that. Then up top, thing I need is what?
T equals 1 is the
Right.
so, yeah.
Given,
U equals 1.
right, times
U equals 1.
probability of u equal to 1, right? Now we'll fill this in. This is, if I do a problem and you guys get it, I'll move on. I mean, hopefully there'll be no uncertainty about this. There's 3 parts to this. This is part A, I believe, right?
Yep.
Okay, so what do we need? We might as well get all this information right now. Probability of u equal 1 is just p, right? Probability, by the way, of u equals 0 is equal to 1 minus p. We don't need it for that part. Probability of t equal 1, well, I'm going to make a comment. Probability of t equal 1 is what? Well, it's p, right, times 1 minus, in this case, v. Probability of this occurring times this weight. Then it's going to be plus probability of that occurring, which is 1 minus p times the cross. That's really the false test. That's probability of t equal 1. And what is probability of t equals 0, guys? I'd make the case it's 1 minus that. If you think about it, there's only 2 possible outcomes. Either it happens or it doesn't, right? But if you were to do it the way he does it in this book, it might be a sanity check. What would you get? Probability of t equals 0, that's down here. Probability of that occurring, which is p, right? Times, what is that? Can y'all read it? I hope you can. Plus probability of that occurring, 1 minus p times the rate, which is 1 minus epsilon. I believe you're going to find out that this is exactly 1 minus that. Because those are the only 2 possible outcomes. There isn't a third. It's not an uncertainty of either. Okay, and what else do we need? We need probability. Let's look at this. Probability of t equal to 1 given u equal 1. All right. So u equal 1, we assume that happens. What's the probability of t equal 1?
1 minus v.
That's right. Just 1 minus. Everybody agree with that? And do we need anything else? I think that's it, right, for this part? Okay, so what do you get?
1 minus v times p on the top.
Well, probability t equal 1 given u equal 1 is 1 minus v, right? And then it's times probability of u equal 1, p, divided by t equal 1 is
All that.
p times 1 minus v plus 1 minus p times epsilon. You have to be attentive to detail on these things, by the way. All right, and you have a solution. I posted these solutions, right? I for some reason, I don't have this problem in front of me. I think I left the other notebook at home down some stuff, the pad at home. I was like, anybody confirm or deny that?
Yeah, that's right.
Yes, right.
You got it. Did you do this one?
I did all those.
Okay, it's a good problem. All right, so that's part A, so we checked that. We'll do let's do, what's the next part? Probability of t equals, or what is it?
Probability of u equals 0 given t equals 0.
And what's the last one? That's almost identical to this.
Probability of u equals 1 given t equals 0, which I think we might have done. Yeah. Oh, wait, no, we didn't. We didn't do that one. Probability of u equals 1
Let's
given
do
t
that
equals
one.
0.
So this is part C. Probability of u equal what?
Yes.
1 given
Yes.
t equals 0.
Yes.
Alright, so this is a drug user that gets away with it. He's not busted, right? So you got a guy who is a user, but the test is false. I mean, it doesn't indicate, it gives him basically says he's not. So downstairs is always going to be P of t equals 0. I hope everybody understands what I'm saying here. I'm just trying to identify whatever that condition is. We need the total probability of that condition occurring on this side. We would normally be multiplying that. Then I have to have what? Probability of t equals 0, right? Given u equal 1 times probability of u equal 1. Does everybody agree with that formulation? Take a moment. Okay, what do I put in here, guys? For probability t equals 0, I can't see it over there, but did I put that down there? What is it?
PV plus 1 minus P times 1 minus epsilon.
Everybody got that? All right, on top, what is the probability t equals 0? Did I put that down there? I don't think I did I?
T equals
T
0.
equals 0.
There, there. The bottom.
No. Probability t equals 0 given u equals 1.
Just do V.
That would just be v.
Pardon me?
That would just be v, correct?
Yeah, well, it's probability of t equal 0 is down here given u equal 1, so it's p times v. And go ahead. So it's p times v, and then it's times probability u equal 1.
V.
Do I have that down there? It's just p. Probability u 1 is equals 1 is p. Wait a second.
Wait, so you said, so in the one we just did, the probability of t equals 1 given u equals 1 was just 1 minus v. It wasn't p times 1 minus v. But now you're saying, in this one, the probability of t equals 0 given u equals 1 is
Well,
p times v.
Well, I mean, what I'm saying is probability of u equal, sorry, look at the probability t equals 0, so we're here, given u equal 1, it's just v.
Yeah.
Yeah.
It's saying,
Yeah.
maybe I
So
heard
it's
it.
not p.
But you're going to end up multiplying it by P. P
So probability of u equal 1 is p. Hold on for a second. I think I got something wrong. So this one, I gotta make sure I got this one. But t equals 0, assuming u equals 1, is just v. I'm sorry about that. And then probability of u equals 1 is p. That's correct. And is that what he has in his book for C? You have this one?
Yeah, that's right.
I'm sorry. I want to tell you one thing though, when you actually do the numbers on this, and he does mention a few things, it's a little troubling if that's any indication of reality. It was for me at least. Usually yield rates and all that stuff and device processing, the tests are much less likely. Any kind of thing like that for reliability testing and stuff like this, you're talking about less than 0.1, 0.01% inaccuracy. Anything but extremely low levels of that inaccuracy would cause huge amount of profit loss. When you're talking about, you know what built-in self-test is? Anybody? All right, well, you're going to get into your senior level courses. That's a real important course in my opinion, because the one thing when you get out and you manufacture large numbers of anything like VLSI processing for chips and stuff like this, that yield rate, which means how many success, that thing makes or breaks everything. Because you can go broke if you have a bad yield and you spent $30 million on everything, and all of a sudden, because these tests, the only way to test these chips, my wife used to work for Intel, and when they go and do testing on these things, they can't test for everything. So they have a select number of components, so basically maybe 0.1% of the batch. And what they'll do is run specific tests on these things, but they can't test for every possibility. And failure rates, especially if they sneak through that part, if something starts failing at a high rate, then they can lose a fortune. Besides that, it's consumer confidence that's crushed, and they'll buy chips from someplace, or buy devices and chips from someplace other than Intel.
We do the part D of this is show these probabilities are consistent with the overall test being 95% accurate. I didn't really understand how to do that when
You know what he's doing? He's summing up.
Yeah, that's all.
He's going to, well, I think what, I said, I believe what he's doing is summing all the possible values of the tests. And I don't have, let me take a look at this. But I believe, I might be wrong about this, but I believe that is summing all those things, and for the accuracy, he's not talking about just the problem of the guys not being a drug user, but he fails the test. He's talking about the sum of all. I believe that's it, but let me just take a look. That's a good question, actually.
I just don't know like where the numbers come from. Is there like no numbers given to us? We're just getting P, epsilon, and V.
No, but all that stuff just cancels if you're summing all of them.
Okay.
This is show the probabilities are consistent with the overall test being 95% accurate. I might be wrong about this, but doesn't he just sum and show that, I mean, if you think about this, the test results, the possible test results, I think that's what he's talking about. Could you do the solutions? I did not do that part.
Should you just sum all the given possibilities? Like U equals
Well, we
1,
saw
T-
that the probability of the first test being false was like, it could be 50%.
Yeah.
Right? We saw, I mean, of somebody who's not a user being identified as a user. So I think what he's doing is that you sum the values of all those tests together. Better be careful about this. So what are there's 4 possibilities that are for outcomes. You can be a user, and it can identify you as a user. Then you can be a user and it misses you. That's second. Then you cannot be a user and it identifies you as a user, and you cannot be a user and it identifies you as somebody who isn't a user. Correct. So you've got 2 correct, 2 false. So if you take a look at the percentage for the outcomes of correct versus the total amounts of outcomes, I think it's 0.95. Isn't that what he does, Ken? In that part?
Yeah.
But I believe, I didn't do that part, but I believe that's what he's talking about. And so, but I'll tell you, sometimes the wording isn't exactly clear what he's looking for. All right, I'm not gonna, did we do 2.7 last time? This is the quiz kind of thing, right? From 2.7, so I'm not gonna touch that later. What I wanna do, and this course, I got to 11, so I'm gonna do it now. I'm gonna move into this, the next part, and I put the PDF notes up, all right, on the actual probability density function and distribution functions and stuff like that. So what I'm going to do is a little different than he has in his book, but it really will give you, and we'll do the problems. I feel a lot of stuff has to, the best way to see it is with problems. Now, let me just do this. Y'all remember when we were talking about, I showed you the histograms, like they had frequency on the bottom axis, or they had a frequency vertical axis, and they had values on the lower axis. And you got these plots that showed you really where are the most likely values of grades or anything were. Do y'all remember those, class? And I said those things could be made into something called a probability density function. Do y'all follow me? So I want to just, do you remember that?
Fit a dog through.
Yeah, we're about to talk about this. So here's one thing that happens in the real world. And I'm going to first start with the probability density function. Then I'll talk about the distribution function. After we gather a huge number of statistics, we can get something called the probability density function. It's PDF. And the probability density function will give us all the information we need to find the likelihood of any kind of a random variable between two values. Now, y'all, I mean, I don't spend much time on this, but what is a random variable in your own words? Something where the outcome is uncertain. But at least we know the possible range, right? Even if the range is infinite. But I mean, we have an idea of the possible outcome, range, and that's a random variable. Coin toss is a good example. It's a binary outcome. It's either heads or tails. If dice, you got 1 out of 6 possibilities every time you roll a fair die. And each one is equally likely, ideally, right? Then there are things that are continuous random variables. And I'm going to start with continuous random variables. So here's what happens. They're going to have something here where you're going to have, on this axis, it'll be the PDF. And I'm going to use x as my random variable. So it's PDF of x. So I'm just PDF. The x, you'll understand it has to be a function of x. And usually, I'll just call it PDF here. It'll be of x. And this is x. So I'm going to just say this is 0, doesn't matter. And it looks something like this. The shape of the curve has nothing to do with it. And it looks like this. The PDF is one thing. It tells me the probability of x being between any two values. Let me just show you what I mean by this. So the probability that x itself is greater than or equal to a, less than or equal to b, is equal to the integral from a to b of the probability density function of x dx. So just basically, if I'm here, and this is a, and this is b, and I want to know the probability that value of x is between a and b, it's simply the integral of the probability density function from a to b. It's a very straightforward idea. Now, where do they get this? They get it from statistical data, usually, or they have some way of doing a forward solver of a known problem, and they get outcomes, and they catalog all the numbers, or the frequency of these outcomes are occurring, and then they get something where they create a proportional fit to something like a Gaussian curve, all right? Everybody follow me? At least an idea. They use some way of generating the data where they can come and get the statistical information. Now, there's one thing about a PDF that's real important. If you integrate over all possible values of the probability density function of x dx, you have to get 1. Or the area under that curve has to be 1. In other words, the likelihood of the event, or of x, if it's a random variable, in between minus infinity and infinity, has to be 1. It's like the coin toss. If we toss a coin, the outcome has to be either heads or tails. Follow me? It can't be a null set. It has an outcome that has going to have a value. This is one of the first things. Now, this is something called the distribution function that in the notes, in our book too, is used. And it's really the integral. So if I want to know the probability of x being greater than, or less than, of x being less than or equal to a, what I'm really doing is this. I'll draw it here. And you'll understand this, I think. So here's my density function, a little picture of it. Here's the probability density function. It doesn't have to look like this. But if I want to know the probability of x being less than or equal to a, I take a here, right? And then, well, I don't know where it starts. It may start at minus infinity. So if I want this probability, it's really the area under this curve. This is my PDF of x. So this is given the symbol f of x. It's a density, it's called a distribution function. Have you heard of this before? If you had this course, if you sat in on this course, or you've been around some of the higher level courses, it's called a distribution function. And that is equal to the integral from minus infinity to, and instead of a, I'm going to call this value x, because that's how he's going to do it. So, probability, I mean, it's called a distribution function right here, because he has an f of x. It's simply the integral from minus infinity to x of the probability density function of x dx. I'm not trying to fool you with any of this stuff, but what it really, this f of x thing is, it's simply the sum, it's really the integral of that PDF all the way up to x. And as x goes to infinity, it has to go to 1. Now, something also that's useful of this, we can do the derivative of both sides, but you can see the actual PDF of x, the probability density function, is just the derivative of the distribution function with respect to x. That doesn't mean a lot to you until we actually do some problems. Make sense to everybody? Okay. Now, there's a couple other things that I'm going to mention, because these things seem very obvious. We're going to do problems so it really fleshes it out. But there are several other things I'm going to throw in that are important to understand. Why we do this. Remember, all this statistical information I'm showing you will be gathered in some way. These curves will be developed. I don't know how. All the time in radar, I have a good idea for some of the things, but they become something that is fairly well known and certain. And some of the stuff is just like almost like the laws of gravity. They always are within these values and stuff like this. So next are some values, some things that are important. There's something called the expected value. This one I'm going to write down. And there's things called the mean too. Now,
Is this stuff coming from chapter 7?
I don't know.
Okay.
I'm looking at the this text, Cooper and McGill, but I can look at, give you a reference in that book too. But it's going to be, I think it's chapter 7. It should be a lot earlier than that. I think it's around chapter 3 or 4.
Chapter 7 have the continuous random variables.
I mean, they will have. It won't. You'll see that it won't matter if they're continuous or discrete outcomes.
I think it's chapter 4.
I did a word search for the probability density function that showed up in chapter 7.
What?
I did a word search.
In that book. No.
Expected value isn't necessarily linked to probability density function.
It is.
Oh, it is. Okay.
You're going to see. We'll do the mean first, and then. But I want to mention something. One second. Okay. I put these. I put the slides up from Dr. Denny of this chapter. This is chapter 2 in the prior book, and I'm going to do this. Before I get into expected value, it's the same thing as the mean, but I'm gonna use the terminology as he uses. So if we talk about things, and these are called moments of, really, of random variable. So when we're talking about moments of anything, what do I mean? Did you all have statics and dynamics? Pardon?
Yes.
You've had? So what's a moment in statics?
It's like almost like a torque, but it's
What do you always have? You have a distance and you have a force, right? And a moment about a point is force times distance, assuming the force is orthogonal to the distance or to the beam length, right? A moment is called a weighted value. So when we take moments of random variables here, what we're really saying is that we want the expected, and I think he does use this, he does use the expected value. And this is a symbol for the expected value. But it's the expected value of what? Here's what happens. Anytime you have x in here, the expected value of x or any functional form of x, and I should do it this way. I'm going to do it a little different than him. The expected operator tells you that whatever is in here, you're going to multiply the PDF by to get the expected value of that whatever. So let me call this some g of x. If I want the expected value of g of x, it's going to be the integral over the entire possible value range of the PDF of g of x times the actual PDF of x dx. What it's really doing is saying I'm going to multiply, instead of a force by a distance, here when I take moments, I multiply g of x here by the density function and I get the value. The first and most common expected value is going to be called the mean value. And when we talk about the mean value, it's the expected value of just x, the random variable x. So the symbol for that is x bar. Remember mean value from anything at all? Like average value, right? You've heard this, right? When I do this, I can simply take the integral of x times the PDF function, whatever it is, of x dx, from minus infinity to infinity. It gives me what would be considered the mean value. Now, actually, when we talk about the average value, I'm not going to get into the median value and things like this. Just understand, this is called a moment, but it's the first moment. Okay. Now there's something called, and this is the mean value. Then there's something called the mean squared value. Now, what is the mean squared value? As the name implies, I'm simply going to take x and I'm going to square it. So it's the integral from minus infinity to infinity of x squared times the PDF of x dx. That would be the mean squared value. And I might as well go ahead and show you one other thing right now.
Mean squared value is not like the bar is removed.
Well, what they'll do is this. Anytime they're talking about a value where it is the average value of an operator, they'll do this. Like that. It'll be, the bar will be over the x squared. Have you heard of these things? Then there's something called a standard deviation. It's probably, you've heard this before, right? I'm going to do it like this. All this stuff kind of falls together. That makes sense. So when we talk about standard deviation, use this a lot on exam scoring. All these values become important. You have large classes, and people want to score based on an assumed curve or Gaussian type of profile. Standard deviation has a symbol sigma, well, sigma by itself, but I should say there's also a thing called a variance. Variance has the symbol of sigma squared. This will become clearer as we get into the problems. With me? It's the last thing I'm going to do before I get into the problems. Now, if you look at this, what this is, the variance is this. It's the expected value, and this is the expected value of x minus the mean value squared. Y'all with me on this, class? So, when I want this, let me just do it this way. If I take x minus x bar and square it, what do I end up with? Well, I end up with x squared. I think everybody sees this. I'm going to have x squared right there, right? Then I'm going to have 2 times x bar, only the minus sign. So it's 2 times x bar. And finally, you're going to have what? Plus x bar squared. Just take a moment. I know I'm throwing a lot at you, but I think it's going to be okay. I think you'll get this. You with me, class? I'm just squaring that. So now I'm going to put that up here. That means the expected value of x minus x bar squared is really the expected value of x squared plus, or really minus 2 x bar times the expected value of x. And then it's going to be plus x bar, the expected value of x bar, and it's expected value of x bar squared. I'm going to talk my way through this one. Can you all follow me what I'm doing here? I'm trying to say I square this thing out here, put it in there, and by the way, anytime you have expected values, if it's expected value of A plus B, expected value of A plus the expected value of B. I didn't show that, but that's the way it is. Now come down here and follow me. Well, remember, that's sigma squared. So sigma squared, which is the variance, is the expected value of x squared. And that's just the expected value of x squared. So I'll just leave it as such. Then it's minus 2 times x bar. Well, x bar is a constant. You all with me? That's a known value. And what's the expected value of x? It's x bar. So it's really minus 2 x bar squared. You all with me, class?
Wait, you said the expected value of x is just the mean value? It's just x bar?
Yeah, right here.
Oh, okay, I see. I thought that bar.
I mean, it's the mean value. It's a constant. Anytime you have, if you want the expected value of a constant, it's the constant. It doesn't change.
Yeah, okay.
All right, now, if you have that, finally, it's minus the expected value of x squared. Well, that just is x squared, or plus x squared, pardon me. Plus x squared. I mean, x bar squared, pardon, x bar squared. You all follow me? And the only thing I've done there is just use the definitions. What do you see about the last two? This just becomes what? Sigma squared is equal to the expected value of x squared minus x bar squared. And what it's usually, the way it's, do you all follow me? The way it's usually written is simply x squared bar minus x bar squared. It'll take you a little bit of time to get familiar with some of this notation, but x squared bar means the average value of x squared, or the mean squared value, and x bar is just the mean value, only you're squaring it. With me? Now we'll do some problems, and I got time to get them done too. Now I put 4 up there, and I'm doing this for continuous random variables, but they can be discrete too. And you're going to see that the only thing that happens, instead of having integration, we have sum, if they're discrete. Were you the one that asked me about July 4th?
Maybe. Depends on if I'm going to be admonished for it.
No. I've got to check with Dr. Nelms, but apparently July 4th is Thursday, right?
Unfortunately, yes. And we had a class on Friday.
Well, and you said, isn't it? You
So
told me
yeah,
you're-
one professor, my thermo, said nah. And then the other professor
Says
said
no?
he said he's not doing class on Friday.
What?
And then the other professor said I'd be convinced to put up a video. So that's fine. That would make me
All right,
think that
now
you could
I'm
be
going to
convinced.
level with you. We have quizzes every Friday. All right, so what I have to do is talk to Dr. Nelms. And what I could do is move the quiz to Wednesday or Monday, if you guys are okay with it. But I have to have like unanimous consent. Why?
Oh, you're asking for consent to move the quiz to Wednesday or Monday?
Yeah.
I was like,
No? You want a Friday?
I'd rather have it Friday.
Well, it's right after July 4th.
It's fine. I'm boring.
What
I'm
about
sitting in
have
my
the
room.
quiz Wednesday and then go enjoy yourself? And you're like,
I'm fine, sitting in my room, chilling. You know,
I have to.
I'm tired of driving and traveling.
I have to go ahead and, level with it. I have to do something for class. I can't cancel.
Yeah.
You get, I mean, that's where you can get home, unless Dr. House says. But I don't think that's. Now, if anybody cancels class, they may not know, they're probably plead ignorance. I didn't know I could cancel. But
I think the teacher's like posting the notes, but just you don't have to come to class.
Well, I gotta check about that. I will check. It's not what you think. It's not so easy. All right. So I gave you, or I posted 4 problems. Just basic things to get you going, get everybody going. They're on there, and this is, so it's 2.21 through 2.24 that I showed you. Did you all see, did you see those things that are posted? So for 2.21, and I'm going to talk about these because we've got a mixture of identifying combinational information as well as actually getting random variable value. Coefficient values and stuff. So for the first one, in 2.21, you got
This
No.
is the
wrong book. Yeah. This is 2.21, and this is out of Cooper. I posted these problems, by the way, and I've got to add one thing to it. So for this one, he has a coin, right? And we have a coin, we're going to toss it 10 times. So 10 tosses of a coin. And what he's asking for is the probability density function for the events that occur, right? And he's saying where k is the number of heads. So you're going to have to just listen now. Anytime you have something where you're going to have outcomes, 2 possible outcomes, and you're going to do that test over and over again, you can use something, these are binomial coefficients. So I put this down before, so write this down. So if we're gonna toss a coin a whole bunch of times, here's what we can do. You could say the likelihood of k heads coming in n trials is gonna be n factorial over n minus k factorial times k factorial. And then it's going to be the probability of the outcome you want, the k, in this case k is a positive outcome, times 1 minus the actual probability that you want of n minus k. And this will give you the actual, has to do with only binary kind of outcomes. It either is going to be heads or it's going to be tails. So if I looked at the probability that I get 0 tails in 10 tries, or 0 heads, pardon, 0 heads in 10 tries, the probability of 0 comma n, or 10, in this case 10, is going to be equal to, and here it's going to be 10 factorial over 10 factorial times 0 factorial. Then the probability of heads is this 1/2, and it's going to be to the 0 power. And then it's n minus k to the 1/2, where it's really 1/2 to the 10th power. Does everybody understand what I've done there? And why it's going like that?
So it'd be 1/2 to the 0 power.
Times 1, there would be what? 1 minus 1/2, which is 1/2 to the 10th power, right?
Okay.
So this is simply going to be 1 over 2 to the 10th power, or 1/2 to the 10th, right? So what is that? 1 over 16, 32, 64. What is that? 512?
1,024.
Is that 1,024? So that would be the actual, I mean, that's the probability of that occurring. You all with me? So here's what he's asking you to do. If I go from 0, where k is plotted this way, and k is the number of heads that occurs in 10 tries, goes all the way out to 10, you're going to see two things happen. First, the lowest chances are at the extremes, here and here. And here you got a value of 1 over 1024, right? Same out here. It'll be a symmetric distribution about the midpoint. That's going to be 1 out of 1024. Then as you keep on increasing it, the most likely event is going to be in the middle, and that's the probability of 5 out of 10 from this thing. What is that going to be? I'm just mentioning this. The probability of 5 out of 10 is what? 10 factorial, right, over, and it's going to be 5 factorial, right? And then 5 factorial, because n minus k is 5, and k is 5, right? Then you have, this is the neat thing, because the probability of heads and tails are the same, this will always be what? Just think about it. If the probability of heads and tails is the same, right, that means this argument p and 1 minus p are the same, right? And it's k times n minus k is n, so it's always 1/2 to the nth there, always. Y'all follow me? So this is going to be 1/2 to the 10th power. This is going to be the greatest probability. As a matter of fact, if I just leave this one over here, it'll make more sense. Just put this as 1/2 to the 10th, and this is 1/2 to the 10th here. And then the middle value, the largest value at 5, is going to be, well, how do I get that? Now this is the way I do this. I know I got 10 factorial, that's 1 times 2 times 3 times 4, all the way to 10. That's 1 times 2 times 3 times 4 times 5. So here I have 6 times 7 times 8 times 9 times 10, right? Over, and then I have 5 factorial. That's 1 times 2 times 3 times 4 times 5. I'm just showing you one way to think about it. We do have this 1/2 to the 10th. Well, I can say I've got 2 times 3 is 6, get rid of that one. And then I have 4 and 8, so that's a 2. Right? And then I got 5 down there. 5 into 10 is a 2. I'm just trying to do it as simply as possible. So I have 2 times 2 is 4, right? And then I have 4 times 9 is 30. It's going to end up being what? That's 36 times 7. You agree? And that means this part is going to be the highest, and it's going to be 36 times 7 times as large as the outer ones. Now, you can fill in everything here, but that's basically what he's asking, to show that. That is a discrete probability density function. If you sum them all, you would get, in fact, the value. Then he asks for the probability of 8 or more heads, right? Or the number of heads be between 2 points, like 6 and 9. Isn't that correct for that problem? In the book.
What is the probability that the random variable is between 6 and 9?
The only thing you do is take this and just take the probability with k equals 6, k equals 7, k equals 8, k equals 9, add them up. That's it. Then he asks the last part, the probability of k is equal to or greater than 8, right?
Yeah.
That's just the probability of k equals 8, k equals 9, k equals 10. And that's it. I mean, in a nutshell. Let's go to the next problem. Go ahead. Yeah.
So real quick, what is the K in this again?
K is the number of heads. It's
Okay.
outcomes that we are looking for.
Okay.
And N is the total number of events.
Events, yeah. Okay.
And the easiest thing to think about is coin tossing.
Yeah.
But you'll use this stuff, you're going to use.
This is an example of discrete random variables.
Yes.
Continuous would be the curve of these.
Continuous would have all possible values in
So
between.
you would integrate it.
And that's exactly. But it's something that just showcases. Next one.
A random variable has a probability distribution function given by.
Hold on for 1 second. I'm going to put it up here. Can you guys just hang with me for another 3 or 4 minutes? Because I want to cover this part. I put out a lot of stuff. Go ahead.
F of x equals 0, or fx of x or something.
Is 0 for weight.
Negative
Capital F?
capital F.
That's the integral of the density function from minus infinity to that value.
And he has
So
a little
capital F of
subscript.
x.
He has a little subscript x
Yeah, that's it. F of x
equals 0 at negative infinity is
at x
less than
minus-
x, which is less than or equal to -1.
What he's doing is this. Right, so he's given a range. From -1 all the way down to minus infinity, it's 0. This is f of x, right?
Yeah.
And then it's going to come up like this.
To f of x equals 0.5 plus 0.5x.
Here we go. F of x equals 0.5 plus 0.5x between.
-1 and 1.
Yeah. So basically, like there's been a constant value of 1, right?
Yeah.
Okay. First, this makes perfect sense. This is true from -1 greater than x less than or equal to 1, and then it's 1 afterwards. So this is a plot of what he discusses. What does he ask?
He doesn't have the equal to. He just has the. Find the probability that x equals 1/4.
It's a great question. Where's 1/4? Right about here?
Yeah.
Well, the probability technically has to be, it would be the value f of x at the upper point minus f of x at the lower. If they give you a single value, it's a continuous random variable, it's 0. Can you with me on that? Just let that thing squeeze down to 0. There's no area under that thing. Follow me?
Okay.
So that part, first part, f x equal 1/4 is exactly, not f of x equals 1/4. The probability that x equals 1/4 is, in fact, 0. Go ahead.
Find the probability that x is greater than 3/4.
Okay, now let's just do this rationally. I'll show you a trick. If we want the probability it's greater than 3/4, right? Well, 3/4 is right here, correct, class? You can say it's the probability of 1 minus the probability of the possibility of distribution function having a value of 1 or greater, minus this. Let me just say something that will help you, and I'm not trying to push it too far. What I would do is get the probability density function right from that. This way you'll see it better, I think. So if I have this f of x, remember I said that the probability density function for x is just the derivative of f with respect to x, right? Remember, f is a distribution function. Y'all with me?
Yeah.
What's the derivative? And this would only be true between -1 and 1. It would be 0 everywhere else. But what's the derivative of that?
1/2.
Just 1/2, right? Now if I were to plot the probability density function for this, it looks like this. This would be the probability density function of x from -1 to 1. It would be 0 anywhere outside of this range, and we have a value of just 1/2, right? This will help you see it, I think. Correct? I don't want to. You with me, guys?
Yeah.
All right. Now, remember, I told you the probability of something occurring is really integrating the probability density function between the values. The lower value is 3/4. The upper value is 1. That area, which is representative, the thing I just shaded, of the probability of x being greater than 3/4 and less than 1. Y'all follow me? Of f of x, or really of the value of x. So what's that going to be? Well, the height is 1/2. What's the width? 1/4. So it's 1/8. I put the answers up, didn't I, for this one?
And so in this case, f of x is just p, and then that is
Well,
probably
this by definition is the integral from -infinity to x of the probability density function of x dx. So that's what they asked for. Do you have access to the solutions? I mean, I know I can look them up, but they're posted online. But don't worry about it if you don't. It's right.
Yeah.
What's the next part?
Find the probability that negative 1/2 is less than x and is less than or equal to 1/2.
All right, hold on. He wants probability. Now here's the range of that. So x being what?
Negative 1/2
Greater than. Right?
less than x.
Negative 1/2.
Negative 1/2.
This is -1/2.
Yes, that's minus 1/2.
All right, so it's x greater than -1/2. Go ahead. Less than what?
1/2. Oh, okay. You look at the perspective.
All right. Well, just look. What's the probability? It's between -1/2. I think you can see it right here. I bet you guys can see it. So if this is -1/2 and this is 1/2, what is it? What's the total width?
1.
1. What's the height? 1/2 kids? 1/2. Can you all see that, class? It's just this area. Now, I like to do this with the PDF because the PDF will make more sense, I think, in some respects. It's easy to do. I know the distribution function, they like going there first, but I prefer this way. But I'm really over. But what's the last problem? The cosine x1?
Yeah.
All right, would you do me a favor, write this down.
Oh, wait.
That should not be the cosine. This is the last problem, 4.
Yeah.
It should be a sine. So change in your notes and make it, do you have that down, by the way, sine? Or no?
It's on the recording, so.
Okay. Make sure it's sine of x, not cosine. It won't work with a cosine. That's an error. And Tom Denny's book even mentions that. I'll make sure the solutions are posted. I know I didn't get the standard deviation and all that. I'll do it next time. And Friday's coming up.
Yeah.
Here's the deal. I'm going to ask you things about these things I just went over in the homework will be related to this on Friday's quiz. Okay? I've got to get some quizzes in right now early because we got a lot of odd things that might happen like July 4th.
You said it'll be related to this stuff, probability density.
I'm going to ask you, tell you, I'll put a note on this, but what I'd like to do, because, I'm going to ask you things about the homework that I assigned, this homework I just, or these problems I just put up, related to the probability density and the distribution function. I won't ask you anything about standard deviation, stuff like that. But I'm gonna ask you to please do the problems and that we're talking about today, just now, and it'll be straightforward. All these quizzes are based on the homework. The last quiz was the homework. See you Friday.
That is Wednesday. Yeah. I got into a good groove last week, and then Memorial Day kind of.
Here's your book. Thank you. Did you understand today? You got this. But I mean, I'm doing this a little differently. I don't know why it is. I feel like I got allergies. Please.
Oh, the new one?
Every single time I've been in this
Did the
class,
computer
I feel like
Could be a mold,
some kind of allergy.